This is John, and he's been training for months to run a 10-kilometer race, and he set himself a goal. He wants to finish the race in under 45 minutes. But that got John wondering, how many runners actually finish a race under 45 minutes? Or put another way, what is the probability that a randomly chosen runner will finish the race in less than 45 minutes? And I always remembered in school, they draw a graph that looks something like this and call it the normal distribution graph. And then they'd say the x-axis represents minutes, and they'd say the average runner finished the race in about 60 minutes, let's say. And that means some runners took a little bit longer, maybe 75 minutes, and others took maybe about 45 minutes. And I thought, well, this is going to be a really easy question. 45 minutes, how long did it take? Well, I'll just find 45 minutes here. I'll just find where the line intersects the graph and go across. And well, this must be the probability right here. But then my teachers would promptly say to me, no, that's not correct. This is not the probability. In fact, the probability is the area under the curve here. And I promptly memorized this and I was able to pass my tests. And I never understood what exactly is the y-axis. So to answer our question, let's break this down into two steps, which will help us achieve our goal of understanding the normal curve and more specifically, what is the y-axis? So we'll start by creating a histogram, which we'll then use to create a density histogram. And once we have the density histogram, that will help us answer the question, what is the y-axis? So let's start with our histogram. And I've brought in some simulated 10-kilometer data to help us fill in our histogram. Each row in this data set represents one runner and the amount of time it takes that runner to finish the race in minutes. So to fill in the histogram, let's define our axes. The x-axis in this case represents 5-minute bins. And a bin is nothing more than a grouping of runners that complete the race within that time period. So in this case, 35 to 40 minutes. And our y-axis is going to be a count of the number of runners that complete the race in that bin. So for example, in our first bin from 35 to 40 minutes, we can see that our runner A and runner B complete the race between 35 and 40 minutes. So that's two. So two is probably roughly maybe about here. And we will draw a bar. And sorry, that looks like more like 4. Let's draw that a little bit lower. Maybe it's more like roughly here. And then let's go to our next bin now, 40 to 45 minutes. So if we go back to our data and start counting the runners, there's going to be 1, 2, 3, 4, 5, 6, 7, 8 runners complete the race between 40 and 45 minutes. 8 is roughly about here. And essentially, we just continue this process until we fill in our entire histogram. So I'll just quickly do that now. Great. I filled in the rest of our histogram, and I wasn't able to fit the full data set on screen. So what I've done is I've added on top of each bar the count of runners in that bin. So for example, in the 35 to 40 minute bin, there were 2 runners. In the 40 to 45 minute, there were 8 runners. And in the 45 to 50 minute bin, there were 16, and so on and so forth. And if we add up all of these numbers here, we'll get the total number of runners in our data set, which is 202. Now, this is great. The histogram shows us a count of runners in each of these 5-minute groupings. But if we look back at our normal curve, we know that the area underneath the curve is the probability. And that means that the total area under the curve has to be 100%. And if we look at the area underneath our histogram, this does not equal the probability. And let's prove that to ourselves. So let's take a look at the area of the first few bins. So we know that the area is equal to the width times the height. So if we look at our first bin here, we know that the width is 5 because each of the bins is 5 minutes. So our width is 5, and our height, the number of runners in that bin, is equal to 2. So that's 10 for our first bar. And if we look at our second bar and try to get the area there, well, the width is always the same. It's always going to be 5. So if we take 5 and we multiply that by the height, in this case 8, well, that's going to be 40. Now, let's take a look at our third bin. So again, the width is 5, and our height in this case is 16. And that is an area of 80. Now, if we're running into a bit of a problem here because we've only covered off the area of the first 3 bars. And if we add up the area we've calculated so far, that's going to equal 130. So we're already way above 100%. And we haven't even got halfway through the rest of these bars. So what we need to recognize here is that in a histogram, the area does not equal the probability. But no problem. What we're going to do next is we're going to make this happen in our density histogram. So here's our density histogram, where the area equals the probability. So to start understanding the density histogram, let's look at what's the same between the histogram and density histogram. So the first thing that's the same is the x-axis. In the histogram, the x-axis represented 5-minute bins, and that is also true in the density histogram. And I'm just going to draw in an example bar here, because the second thing that's the same is how we calculate the area. So in the histogram, when we calculated the area of a bar, the area is equal to the width of that bar times the height of that bar. And that's also true here in the density histogram. So if we take the width and we multiply that by the height of the bar, that also represents the area. So those are the two things that are the same. The x-axis represents 5-minute bins, and how we calculate the area of the bar is still the width times the height. So what's the difference then? If the width is going to be the same because it's 5-minute bins, and how we calculate the area, that's also the same. So the only difference, the only thing that we can change is this h here. And to be clear, that's going to be this h in the formula. So in order to make the density histogram, we need to understand what exactly is the height in the density histogram. In order to understand the height, we need to understand what is the probability of being in one of these bins. And that is just the number of runners in a bin divided by the total number of runners. So for example, we know the total number of runners in our data set is 202. And if we wanted to know the probability of being in this first bin here, that would be the number of runners in the bin, 2, divided by the total number of runners, 202. But remember, we need to find a way to make that probability equal to the area. And luckily, we now have 2 formulas that we can use to make that happen. So our goal is to make the area equal to the probability. And we know what the area is. That's the width times the height. And we know what the probability is. That's this right here. The number of runners in a bin divided by the total number of runners. And now we just have to isolate for height. And to do that, we just have to multiply both sides by 1 over w. And that cancels the w's out here and multiply by 1 over w here. And now we have what the height equals, which is n over t times 1 over w. Great. So, but this is just a bunch of letters. So what actually is this? So n over t, we know that that is the probability, n over t. So we can say that that is probability. And that's going to be all over this part here, w. Now, to make it general, w is going to be whatever the unit of your x-axis is. And in our example, that happens to be minutes. So now we know what the height is, and we can answer the question, what is the y-axis here? Well, that's going to be, in this example, probability per minute. Awesome. So let's now fill in our density histogram. I'm just going to clean this up, and then what we'll do is we'll use this formula to fill in the density histogram. So I've cleaned up the screen a little bit. Now let's plug in the numbers from our histogram into our formula here. And let's see what happens. Let's use the first 3 bars. So starting with this bar here, if we want to find the height on the density histogram, then we take the number of runners in the bin, which is 2, divided by the total number of runners, 202, and we'll multiply by 1 over the width, which we know is 5. And that is equal to 0.00198, 0.00198. And let's do our second bar. So that's this one right here. There's 8 runners in that bin. Divide by the total number of runners, and again multiply by 1 over 5 minutes. And that is equal to 0.00792. Okay. And finally, let's also do this third bin that has 16 runners in it. So if we take the height is equal to 16 divided by 202 times by 1 over 5, and that is equal to 0.0158. Okay, 0.0158. Well, and I should say these are all approximately. I just went to, how many decimal places? So 1, 2, 3, 4, 5, to about 5 decimal places. So with these first 3 bins calculated, we can start to graph these on our density histogram. So we know the y-axis. Okay, let's put 0.010 maybe here, and then about here would be 0.020. Okay, then maybe up here we can do 0.030. And again, this is probability per minute. Probability per minute. So the first bar is about 0.00198. So that's about 2. That's going to be, maybe somewhere around here. And then, so that's the first bar. And our second bar is going to be about 0.8. Maybe that's approximately about here. And our third bar is about 0.015. So maybe all closer to 1.6, maybe about there. All right. And essentially, we can just continue to fill in our density histogram in this same way. I'll just quickly complete that, and then we'll look at the density histogram and see if we can understand what's going on. So I've now filled in the rest of our density histogram, where the area equals the probability. But let's take a closer look at that. So let's say we wanted to calculate the probability of being in this 40 to 45 minute bin. Well, that means we need to take the area, which is the width times the height of this bar. So the width we know is 5, and the height is 0.079, sorry, 0.00792. Just check that. We calculated that in the last one, 0.00792. And that's going to equal 0.0396. Or about a 4% probability that a random runner would, from our data set, would finish this race in the 40 to 45 minute bin. Now, how can we verify that? Well, if we look at our histogram, we know that the probability of being in this 40 to 45 minute bin is the number of runners in that bin, which is 8, divided by the total number of runners in our data set, which is 202. And if we do that calculation, we will also get 0.0396, which matches our area. So that's perfect. So now we have verified that the area is indeed the probability. And this is true for all of these bars because our y-axis is now a probability per minute instead of just the raw counts that we had in our histogram. And this probability per minute is what's known as a density, and that's why this is called a density histogram. Now, you may have noticed that we can answer John's question now about what's the probability that a random runner would finish this race in less than 45 minutes, because we've calculated the area here. So all we need to do is take the sum of the area less than 45. So let's do that. So if we wanted to calculate the probability here, well, that's going to be the same width, which is this width here, which again is 5. So we'll just take the 5 and we'll multiply that by the height, this time the height of the first bar, which is 0.0019. 198. And if we do that calculation, we're going to get 0.0099. Now, all we need to do is add this probability to this probability. So that will be the sum of the area less than 45 minutes. So we'll take 0.0396 plus 0.0099, and that equals 0.0495, or about 5%. So there's about a 5% probability that a randomly chosen runner from our data set will finish this race in 45 minutes. Now, that's great for John, but we still haven't answered our question of what is the y-axis in the normal curve. So now let's go from the density histogram to the normal curve. So to get from our density histogram to our normal curve, let's imagine that instead of having only 202 runners, we had thousands or maybe tens of thousands of runners. Then we would have enough data to fill in more narrow bins. And by that, I mean, instead of a 5-minute bin, let's imagine we had a 1-minute bin instead. So our bins would be more narrow. So, we'd have maybe smaller bins that look something like this. And you can see that if we continue to imagine getting more and more data and making the bins more and more narrow, what we'd eventually see is the tops of each of those bins would become a smooth curve like this, which is approximated very well by our normal curve. And all we need to do then is if we begin to get rid of our density histogram in the background, what we'll be left with is the normal curve that is approximating very well our data set. And the key point to recognize is that our y-axis didn't change. It is still probability density, or in the case of our example, probability per minute. So the y-axis doesn't change between the density histogram and the normal curve. It always represents probability density or probability per unit of your x-axis. In our case, probability per minute. So now we can answer two questions. We can answer John's initial question, which was what's the probability a random runner finishes in less than 45 minutes? And we can answer that in sort of two ways. So in our density histogram, we calculated the area of the bars that are less than 45 minutes, and we calculated approximately 0.0495. But we can also answer this question using our normal curve, which is modeling our data set. So again, we just need to calculate the area under 45 minutes. And when I calculated this area with the calculator, I got about 0.048. So actually, yeah, the normal model is approximating our data set really well. It's pretty much the same. We get about 5%. So to answer John's question, the probability that a random runner from our data set will finish the 10K race in less than 45 minutes is about 5%. And then to answer our question, which was what is the y-axis on the normal curve? Well, it's the probability density. Probability density. Or the probability per unit of the x-axis. In our case, so in our example, that was probability per minute. I hope that helped you understand probability a little bit better, and thank you so much for watching.